talked about several different methods of solving quadratic equations. In the last part of this lesson, I'm going to talk a little bit about what the quickest method might be to solve a particular quadratic equation. So let's start with an example. Here's my equation. It's the product of 3x plus 2 and 2x plus 5, that equals -5. Now, although the left-hand side is nicely factored for us, the right-hand side is not 0. So I certainly don't want to apply the zero product property right off the bat. So am I going to use the quadratic formula to solve this equation? Well, once written in the appropriate form, any quadratic equation can be solved using the quadratic formula. What's the appropriate form? ax squared plus bx plus c equals 0. In this case, I think I will use the quadratic formula. So I'm going to start by rewriting this equation into standard form. So what I'm going to have to do is expand that product on the left-hand side. So foiling those binomials, I get 6x squared plus 15x plus 4x plus 10 equals -5. Combining the linear terms and adding 5 to both sides of the equation gives me a quadratic equation in standard form. Now I'm going to use the quadratic formula. So in this case, a equals 6, b equals 19, and c equals 15. So I have x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a. Now at this point, I'm going to pull out a calculator to evaluate the expression under the radical. So I have 19 squared minus 4 times 6 times 15, that equals 1. So I'm going to be able to simplify from here. So I have -19 plus or minus the square root of 1 over 12. So I have two solutions. X equals -19 plus 1 over 12. That is -18 over 12, which is -3/2. There's one solution. Or x equals -19 minus 1 over 12, which is -20 over 12, which is -5/3. So before I check these, I just want to talk about a couple of things here. We ended up with rational solutions. And whenever the quadratic formula yields rational solutions, the equation could have been solved by factoring. That doesn't mean I had to have used factoring, but I could have solved the quadratic equation by factoring. Well, how would that have looked? So starting with the original equation, doing exactly what I did to use the quadratic formula, I put the equation into standard form with the right-hand side equal to 0. And then I think, are there integer factors of 90 that add to 19? Well, there are, 10 or 9. I'm going to use those integers to factor this trinomial on the left by grouping. So going through that process, I end up with the factorization 3x plus 5 times 2x plus 3, and that equals 0. Applying the zero product principle, I get two linear equations. And when I solve the linear equations, I get exactly the same solutions as I got from using the quadratic formula. Which method is easier or quicker? They seem about the same to me in this case. But now let's go ahead and check our solutions. In this situation, I think I'm going to use my calculator to do the check. So I'm going to check -3/2 first. So when I check this, I'm going to enter my expression on the left just as it is in my equation. Parentheses, 3 times my x value, which is -3/2. So I'm going to put my fraction in parentheses, 3 divided by 2, make it negative, plus 2, close parentheses. Now I want to multiply that by 2x plus 5. So times, open parentheses, 2 times -3/2 plus 5, close parentheses, that equals -5. That solution checks. Let me check -5/3. 3 times -5/3, so I'm going to put that in parentheses, plus 2, close my parentheses, times the second factor, 2 times -5/3 plus 5, and that equals -5. So both solutions check. So the solutions are -3/2 and -5/3. Here's a similar equation, except now the right-hand side is 0. Am I going to use the quadratic formula to solve this equation? I don't think so. It would be a lot more work than I need to do. I can apply the zero product principle directly. So here's my equation. 3x plus 2 times 2x plus 5 equals 0. This tells me that 3x plus 2 equals 0, or 2x plus 5 equals 0. So I have x equals -2/3, or x equals -5/2. Now I skipped a step solving those linear equations, and it might help to go back and work through all the steps just to see where I got those values for x. So now let me check my solutions. So here, the check's a little bit easier. So for example, if x equals -2/3, then the expression 3x plus 2 equals 3 times -2/3 plus 2, and 3 times -2/3, that's -2 plus 2, that equals 0. Now that's enough of a check, because now I have 0 times some number equals 0. That's all I need. Let's check the other solution. If x equals -5/2, now it's going to be the second factor that's 0. Then 2x plus 5 equals 2 times -5/2 plus 5. That's -5 plus 5, which equals 0. The second factor is 0 in this case, so the product must be 0. So the solutions are -2/3 and -5/2. Here's another equation. Am I going to use the quadratic formula to solve this equation? Well, I certainly could, but the left-hand side of this equation looks like it can be factored fairly easily. So I'm going to factor and then use the zero product principle. Now the reason why I say this is an easy factoring problem is I see I have a common factor of 3x in both terms, leaving behind a factor of x minus 4. So either 3x equals 0, so I have x equals 0, or x minus 4 equals 0, so x equals 4. Let me perform a check. The check for 0 is very easy. 3 times 0 minus 12 times 0, that's 0 minus 0, is 0. Let me check 4. If x equals 4, then 3x squared minus 12x equals 3 times 4 squared minus 12 times 4. 3 times 16, that's 48, minus 12 times 4, that's 48. That indeed equals 0. So I have two solutions. The solutions are 0 and 4. Now before I do another example, I'm going to just show you what work would be required to use the quadratic formula for this equation. So what we have here is the values of a, b, and c. A is 3, b is -12, and in this case, the constant term c is 0. Plug all these numbers into the quadratic formula, get my two solutions, evaluate them separately, and indeed I get 4 and 0. In this case, I think that factoring is definitely a little bit quicker, but that's just my preference. Here we go again. Am I going to use the quadratic formula to solve this equation? Now here, my answer is no, because I see I have to do a lot of work even to get this equation into the form to use the quadratic formula. And the reason why I know there's a quicker method is because I have x minus 5 quantities squared. I can solve this using the square root property. So let's do that. So I'm going to start by isolating my square, which is x minus 5 in this case. So dividing both sides by 2, I have x minus 5 squared equals 16. Now applying the square root property, I know that x minus 5 equals plus or minus the square root of 16. So this gives me two solutions. X equals 5 plus or minus 4. So x equals 9 or x equals 1. So let me perform a check. If x equals 9, I'm going to go back to my original equation, 2 times 9 minus 5 squared. That's 2 times 4 squared, and 2 times 16 is 32. That's indeed what I wanted on the right-hand side. If x equals 1, then 2 times x minus 5 squared is 2 times 1 minus 5 quantities squared, which is the square of -4. 2 times 16 again is 32. So both my solutions check. So the solutions are 1 and 9. Now I'm going to give you an idea of just how much work would be required to use the quadratic formula. I need to put this equation into standard form. So the first thing I need to do is expand x minus 5 quantities squared. So that's going to be x squared minus 10x plus 25. Multiply that trinomial through by 2. And then subtract 32 from both sides. So at this point, I'm ready to go ahead and think about using the quadratic formula, or perhaps solving this by factoring. But it was so much easier to use the square root property, at least in my opinion, for this equation. So here's another example. Am I going to use the quadratic formula to solve this equation? Well, what other methods do I have? Well, this one I can't solve using the square root property, but perhaps I can factor it. I'd have to find integer factors of -200 that add to 35 in order to get a start at factoring the left-hand side. Well, I actually solved this quadratic equation in a previous lesson using factoring, and it actually took me quite a while to come up with the integer factors that would work. So in a situation like this, I would probably use the quadratic formula. So let's do it. So for this equation, a equals 2, b equals 35, and c equals -100. My variable's w, not x. So when I write down the values for w using the quadratic formula, I have w equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Once again, I'm going to pull out my calculator to evaluate the expression under the radical first. I have 35 squared minus 4 times 2 times negative 100. That's 2025. I think this might be a perfect square because it ends in 25, which is a perfect square. And when I hit the square root, I see indeed it is. It's 45 squared. So when I sit down to simplify this, this is negative 35 plus or minus 45 over 4. So I have two expressions to evaluate for w. W equals negative 35 plus 45 over 4, which is 10 over 4, or 5/2. The other situation is that w equals negative 35 minus 45 over 4, which is negative 80 over 4, or negative 20. So I have two values for w to check. So when I do my check here, again, I think I'm going to check using my calculator. Now here I wrote 5/2 as 2.5. And I did that because that's an exact decimal form of 5/2. So I'm going to check 2.5. So I have 2 times 2.5 squared plus 35 times 2.5 minus 100. That equals 0. Let me check my other solution, negative 20. So I have 2 times, I'm going to put my negative 20 in parentheses before I square it, plus 35 times negative 20 minus 100 equals 0. So both solutions check. The solutions are 2.5 and negative 20. So now let's kind of summarize some of the things we observed in the first part of the lesson. When the left side of the quadratic equation can be factored easily, in this case, I would probably factor that left side and use the zero product principle in order to solve the equation. If the quadratic equation has no linear term, if b is 0, then, in this case, I'm going to isolate the square term and use the square root property to solve the quadratic equation. There's another form where I'm going to use the square root property, and this is where I have something like 5x minus 2 quantity squared. Again, I'm going to use the square root property. But if the left side of the quadratic equation cannot be factored, or I can't factor it easily, in this case, I pull out the quadratic formula. So now we're just going to make some choices as we are asked to solve some quadratic equations. So here's my first equation. Now, if I'm going to solve this using either factoring or the quadratic formula, the first step is to write it in standard form. That's with 0 on one side of the equation. So I'm going to start by subtracting 4 from both sides. Now I like to factor, so I'm going to ask myself, are there integer factors of negative 12 that add to negative 11? There are, negative 12 and positive 1. So I'm going to make the choice to solve this by factoring. So I'm going to rewrite the linear term as negative 12x plus 1x. And now I'm going to factor by grouping. So I have a common factor of 3x in the first two terms that I could pull out, and the last two terms have a common factor of 1, which I'll pull out for emphasis. And now I see I have a common binomial factor of x minus 4 in both terms, leaving behind a binomial factor of 3x plus 1. Now applying the zero product principle, I know that x minus 4 equals 0, or 3x plus 1 equals 0. So I have two equations, x equals 4 or x equals negative 1/3. Now I want to check. So if x equals negative 1/3, then 3x squared minus 11x equals 3 times negative 1/3 squared minus 11 times negative 1/3. The square of negative 1/3 is 1/9, so I have 3 times 1/9 plus 11/3. 3 times 1/9, that is 1/3 plus 11/3, which is 12/3, which reduces to 4. That's indeed what I wanted. What if x equals 4? If x equals 4, then 3x squared minus 11x is 3 times 4 squared minus 11 times 4. 4 squared is 16. 3 times 16 is 48. Subtracting 44, that's indeed 4. That's what I wanted. So my solutions check. And the solutions are negative 1/3 and 4. Now, it would have been okay to solve this quadratic equation using the quadratic formula, as long as the method isn't specified. And here I was just told to solve using any method I choose. So let's solve x squared minus 3x equals 1. Now, I certainly can't use the square root method here because I have a linear term. So I'm going to start by rewriting this in standard form. So I'm going to start by subtracting 1 from both sides of the equation. Can the expression on the left-hand side be factored? Well, in this case, the answer is no. There are no integer factors of negative 1 that add to negative 3. I've got to use the quadratic formula. So x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Simplifying, I have 3 plus or minus the square root of 9 plus 4 all over 2. So this is 3 plus or minus the square root of 13 over 2. Notice that I could not factor the trinomial on the left-hand side. And in this situation, I ended up with irrational solutions. Let's check our solutions. I'm going to pull out a calculator to do the check the way that Steve was showing you in the previous part of this lesson. So I'm going to start by clearing out the memory in case any of Steve's solutions are still there. So I'm going to clean out my memory, and I'm going to enter the first of my 2 solutions. So in the numerator, I have 3 plus the square root of 13, close the parentheses, divided by 2. Now I'm going to add that to the memory and clear my screen. Now I'm going to evaluate x squared minus 3x and hope I get 1. So calling my number out of memory, squaring it, there's x squared minus 3 times x equals 1. The solution checks. Let me check the second solution. So now I have 3 minus the square root of 13, close the parentheses, divide by 2, add that to memory, clear my screen. Now I need to evaluate x squared minus 3x. So there's my x squared minus 3 times x equals 1. Both solutions check. So the solutions are 3 plus or minus root 13 over 2. Here's another one. Now in this situation, there is no linear term. I could isolate the x squared, and I'm going to do that. I'm going to use solving by the square root property. So to isolate x squared, I'm going to start by adding 100 to both sides, then dividing both sides of the equation by 5. 100 divided by 5 is 20. Now using the square root property, I know that x equals plus or minus the square root of 20. And I'm going to just simplify this radical because I showed you how to do that in the last lesson. I just want a little bit more practice. So 20 has a perfect square factor of 4. So I have plus or minus 2 radical 5. So now I want to check my solution. I'm going to do my check up here. If x equals plus or minus 2 root 5, I need to check that 5x squared minus 100 equals 0. Now in this case, I can do both checks at once, because when I square either positive or negative 2 radical 5, I'm going to get the same thing. So 5x squared minus 100, so I have 5 times 2 radical 5 squared minus 100. So I have 5 times 2 squared times radical 5 squared minus 100. So let's see, I have 5 times 4 times 5 minus 100, and 5 times 4 is 20, times 5 is 100, and 100 minus 100 is 0. So my solutions check. So I can state my conclusion. The solutions are plus or minus 2 root 5. Here's another example. Now here I do have a linear term, 40n. So I'm going to solve this either by factoring or using this quadratic formula. I think I'm going to solve this by factoring. And to do that, I'm going to start by subtracting 40n from both sides. Now the reason why factoring seems like the most logical choice is I see that there's a common factor to the two terms that I can factor out quite quickly. So now I see there's two possible solutions, n equals 0 or n equals 4. Let's do a check. Here, the check is so quick, I'm just going to do it in my head. When n equals 0, the left-hand side evaluates to 0. When n equals 0, the right-hand side also evaluates to 0. So clearly, 0 is a solution. How about when n equals 4? Well, 4 squared is 16. 16 times 10 is 160. 40 times 4 is 160. So both solutions check. So the solutions are 0 and 4. X squared equals 7. This one begs to be solved using the square root property, so that's how I'm going to do it. If x squared equals 7, then I know that x equals plus or minus the square root of 7. And here the check is very easy. If I square either positive or negative root 7, I get 7. That's the definition of the square root. So I have my solutions. The solutions are plus or minus the square root of 7. So you're probably thinking, why did I bother with this example if it's so darn easy? Well, you know what? We could actually solve this by factoring. And the way we're going to solve it by factoring is to recall that when we square a square root, we get the radicand back. So let me show you how I'm going to use this. I'm going to rewrite the equation as x squared minus 7 equals 0. And I'm going to rewrite 7 as a square. This is radical 7 squared. Now I have the difference of squares. So factoring the difference of squares gives me x plus radical 7 times x minus radical 7. Now when we were factoring earlier, we didn't include irrational numbers in our factoring. But if we do include irrational numbers, and we can do that mathematically, we can apply the zero product principle at this point and we get our two solutions. Either x plus radical 7 equals 0 or x minus radical 7 equals 0, and we get the same two results. X equals the opposite of radical 7 or x equals radical 7. So I just wanted to point out that we were restricting ourselves a little bit when we were only factoring over the integers. 4x squared plus 25 equals 0. Again, I think I'm going to apply the square root principle. Isolating x squared, start by subtracting 25 from both sides. And at this point, Steve's guy with the flag is kind of over in the corner, but I'm going to keep going. And I confirm that indeed I do have a negative number on the right, and if I apply the square root property, I'm going to be attempting to take the square root of a negative number. And I can't do that when I'm working with real numbers. So this is a quadratic equation that has no real number solution. So the equation has no real number solutions. So that ends lesson 14.